Nice.
Great, so let's get started. We're very happy to have Lieke here with us doing the CETA seminar today. Lieke is currently a third-time research fellow at the Center for Computational Astrophysics at the Tyler Institute of New York, and also a Spitzer fellow at Princeton, as well as, a fellow at the Princeton Society for Physics. That's right. Okay. And Lieke is an expert on the lives and deaths of stars, especially massive stars, and especially massive stars and binaries, which is why a lot of her work actually connects to gravitational wave populations that we see in the LIGO detectors. She's worked in the past on a bunch of problems, or very, very interesting problems. For instance, the origin of this peak of the black hole mass function at roughly 10 solar masses, redshift evolution of the mass distribution of binary black holes, and today she'll be telling us about beyond the first waves, where we stand in understanding binary neutron star and binary black hole formation. So thanks again, Lieke, and take it away.
Thank you so much, and thank you so much for having me. It's been really fun, quite a busy schedule. I'm happy, as I mentioned, I was afraid maybe there was too many Americans here and they would all be gone for Thanksgiving, but that seems to be all right. At least I'm quite happy to meet a lot of people. Throughout this talk, before I start, please interrupt me. I much prefer having questions throughout the talk than everyone saving everything towards the end. So if I don't make it to the end, I take that as a compliment. But also if I do, I should be able to make it to the end, so it should be fine. I don't have that many super long slides. And yeah, today I want to talk a little bit about beyond the first waves. After the first waves of gravitational wave detections, where are we today with understanding binary neutron star black hole formation? Sometimes if you're in the field, it might feel like we just have way more questions risen than we have answered. But I want to show a few things where I think we have actually made some progress and have some interesting results. Of course, it's going to be a super biased view of my opinion, but take that in the back of your mind. Okay, before I dig into it, we are now almost at the end of the first decade of gravitational wave astronomy. Next year is the 10th year anniversary of GW 1509-14, which of course was in 2015, which was the real starting gun of gravitational wave astronomy, and it feels like so much has happened since then. We've used gravitational waves to place constraints not only on the stellar mass black hole function, on the rates, but we've also been super lucky, really super lucky, with the first binary neutron star merger, GW 1708-17, which helped us constrain equations of states, showed that they are sources of our process materials and of GRBs. And it really, I think most importantly, showed us how gravitational waves and electromagnetic observations together can really give us a full picture of how the universe works. But since then, we've been detecting more and more systems, and now we have about 19 gravitational wave detections in Gallup 3, depending on who you ask. And we have 162. I just checked right before this talk. I think the current counter of 04 is 162 additional systems detected in 04. So for me, that's particularly exciting because it means that we're moving from this initial phase of discovery, which is amazing, but we're really focusing on these individual systems, to an era where we're focusing on population studies and trying to understand the normal black holes and the normal neutron stars. Like, what are these populations of black holes and neutron stars telling us about their progenitors, which are massive stars? Now, of course, this is just the beginning. This is a really nice plot from Tom Callister from his contributed paper this year, where you see these three waves growing a lot from 1 to 10 to 100 order of, and now we're growing a little bit slower, but we keep on going. But in 04A will be released in the next half year. They have to, because as people here probably will know, they have to release the data by the summer. But if you plot the prediction given the current rate of the number of systems that we will get in the future, we are indeed like tripling-ish the current size of the catalog, but with next generation and third generation or next generation, however you want to call them, detectors, we're going to go to tens of thousands to even millions of detections per year. Now, one of these three lines, which is the binary neutron star mergers, sadly, very much at the lower end of the statistical uncertainty. This kind of shows the uncertainty that we have in the rate. So I don't know if in the end we're still really going to detect more neutron stars than we are going to detect binary black holes, but we'll see. I'm very interested in what the updated rate predictions will be in the next coming year. But in any case, we have so many detections. Think about X-ray binaries, which were all the stellar mass black holes we could see before gravitational waves. We had of the order of tens. And now suddenly we have hundreds times 2. And so we really have a population of fossils of massive stars. And this raises one clear question: how did they form? Because gravity is pretty weak, and so to get two compact objects to emit gravitational waves, you have to place them really close together. So close, in fact, for example, 10 solar masses black holes have to be less than 10, 20-ish solar radii, but the progenitor star of a 10 solar mass black hole is like thousands of solar radii. So it would never, ever fit in that final separation. So the question really is, how do you bring the cores of massive stars really close together, or their remnant compact objects really close together, either through interacting these stars or through their environment? So this is kind of known as the separation problem, and luckily theorists are very creative, so many different formation channels have been proposed, which in essence all try to address this problem. They all try to say, how do you bring these compact objects close together? And very broadly, you can subdivide them between isolated binary channels, which are channels that assume that you have the stars born together in a binary pair, and they get their cores close together through binary interactions like mass transfer or tides, and dynamical formation channels that assume that you're born in a dynamical environment and you can exchange or get your cores close together through dynamical interactions. Now, if we know which of these formation channels is dominant, we can hopefully learn something about the progenitor or the environment in each of these very interesting formation channels. Like, there's a lot of things unknown about AGNs, a lot of things unknown about stars, and so for the longest time, for the past 5 years, I would say, the mentality has been like one channel to rule them out all. Which of these formation channels dominates the merger rate that we see? And can we kind of constrain the mixing fraction of how much all of these different formation channels contribute to the merger rate that we have? But as people got more and more creative, they also just created more and more formation channels. And conspicuously, all of these formation channels seem to kind of predict a rate that is of the order or even higher than the observed LIGO-Virgo rate. So this is the LIGO-Virgo rates from the first few detection campaigns, observing runs. And so this is a beautiful review by Flor Boekgaarde and Ilya Mandel. And so I'm going to play this where you see each of these lines is a study, and each of the colors is a different formation channel. And as if you see, most of them or a lot of them can produce of the order or sort of 100% or more of the detected gravitational waves. Now, obviously, that is a bit problematic because if everything does everything, we have way too many gravitational waves. We have a missing gravitational wave problem. So probably, yes, go ahead.
What's the primary reason why these rates are over?
Yeah, so I think for the isolated binary channel, a lot of this here is that they make very optimistic assumptions about common envelopes that I think should be gone. So I think that will lower a lot of this. If you want to know about the other ones.
No, this was the main thing.
Yeah, I think for isolated, one of the biggest issues is that people assume that common envelopes or massive stars always succeed, and I think that's wrong. But we're moving on. Great question. Okay, so what do? Well, maybe we shouldn't just look at the rates, because of course we don't just get rates, we get other properties of these emerging compact objects. They have masses, they have spins, they have mass ratios, etc. And so the thing that I look at most currently is the mass. And that is because the mass is by far the best measured property that we have. And so this is my cartoonish version of the LIGO data. It's not the real data at all, so ignore it or don't take it seriously. But, you know, broadly, there is some like number of binary neutron stars merging at the lowest masses. Then there's some mixture of neutron star black holes in those kind of intermediate masses. And above some mass, you expect that mostly it's just binary black hole mergers. Though this is in primary mass, you know, there's complications with the mass ratio, etc. But the interesting thing that I found is that the higher you go in mass, the more formation channels contribute. Especially, maybe this is a sociological thing, I don't have an answer, but especially where we're very sensitive to gravitational wave data, we have a lot of formation channels contributing. But we can also flip this around, because I think it's very interesting to look specifically at this side, where it seems that there's only very few or possibly only one formation channel contributing. And so before I go into that, I do want to make a comment that the game from here on out is probably going to be more and more, how do we properly cut out parts of the data that we think are coherent populations? For example, how do we properly cut out the 35 solar mass peak and think about the other properties of those systems in the peak, like their mass ratios, not just their masses, but mass ratios, spins, etc. And does that correspond to any of the predictions of these formation channels? So not just the rate and not just one property, but the full, as many dimensional things as you can get your hands on properties of the data. And I want to highlight that Shumendra Roy, a PhD student of Will Farr at CCA, is currently thinking about that as well, but I know a lot of people here are thinking about similar problems. Yes?
I want to contrast this plot with the plot from Ilya and Flor's paper review that you showed, because in that plot, almost all of the channels and all of the different predictions sort of straddle the true measurement, right? But here we see that most of the channels, except for like isolated binary, stable mass transfer channels, have these are producing these higher mass systems, which naturally have like logarithmically lower rates.
Yes.
So doesn't that mean that those channels are all poor predicting?
Yes.
Even if you believe that they are the only channel that.
This is a biased opinion, but yes, I think this is you're taking exactly the right thing away, because these nuclear, like these dynamical formation channels, they all predict to peak at higher masses. None of them really predict to peak at like 9 solar masses, which is where we know that the majority of the binary black hole mergers come from. So I think it was logical at first to ask, like, what is the mixing fraction that we have, and can we like do something like that? But if you just look at the masses and the other properties now, I would say, well, it's obvious that, I don't know, if the AGN channel or even chemically homogeneous evolving stars would dominate, then why would we have a peak at 9 solar masses? That doesn't make any sense. So in a sense, that to me already says maybe these kinds of systems are an order of magnitude more common than kind of these sort of dynamical formation channels. But both I think both from that previous plot that I just showed from Ilya and Flor, both these and these rates are over-predicting. Like a lot of those isolated channels are also way over-predicting. So there's just no real constraining power in just looking at the merger rate. Questions? Okay. So then let's think about that low mass peak. Why do we think that binary neutron stars form mostly, if not exclusively, through the common envelope channel? And well, part of that is what we've just been talking about. It's basically, it's basically that a lot of these dynamical formation channels or all these other channels, they just do not manage to form, they do not predict to form low mass black holes. They, let alone binary neutron star mergers. For example, chemically homogeneous evolution only works for stars that are at 0-ish main sequence, more than about 20-ish solar masses. The higher mass you are, the easier you get mixed. And these lower mass stars just don't mix well, and so they don't form binary neutron stars. Clusters, they really missed the low mass peak. There was a recent paper from Antonini and Felix where they also highlighted that they could produce stuff more towards 30 solar mass, but they really missed that 9 solar mass peak because the low mass objects are ejected and they don't really contribute to the merger rate from these dynamical environments. AGN disks, maybe a bit of a big question mark because they can do almost anything, but if anything is a prediction from AGN disks, it's usually that they can form these really massive, almost intermediate mass black holes, which is again, very far from binary neutron star mergers. So there's only 2 formation channels that are still in the running for these lowest, for the binary neutron star mergers. And those are both isolated binary evolution channels, namely the stable mass transfer channel and the common envelope channel. And we call them that because isolated binary evolution, like classical binary evolution, can broadly be subdivided into these 2 categories based on the mass transfer that they go through. Because the mass transfer really is the way in which you determine your final separations and your final masses and how you exchange your momentum with the orbit. And so that's why they really define the formation channel. And one of them is where if you go through only stable mass transfer throughout the whole evolution, we call it stable mass transfer channel, nothing weird. And if at one point throughout the evolution you go through unstable mass transfer, we say you go into a common envelope, then we call it the common envelope channel. And now I'm going to convince you that for binary neutron stars, this channel, the stable mass transfer channel, also fills because it kind of has a minimum mass that it can produce, and below this, it becomes impossible to form merging compact objects with the stable mass transfer channel. The reason for that lies in the criteria for the mass transfer to be stable. So the fun thing about the stable mass transfer channel is that you can kind of cartoonishly draw out the evolution of these binaries and kind of define just core important phases of their life, which are mostly this first mass transfer from star to star and the second mass transfer, from star to compact object, which we've just said are both stable. But the criteria for stability is heavily dependent on mass ratio. What exactly the stability is and how it works, there's a lot of questions, a lot of work, but everyone kind of agrees that if you have a much more extreme mass ratio, at some point your mass transfer will become unstable. So there's some critical mass ratio beyond which this channel no longer works. And that means that we can take this inequality and use it to place constraints on which masses and mass ratios can join in on this channel. I won't bore you with the full derivation, but essentially you can kind of distill a minimum black hole mass that you can form as a function of the ZAMS mass ratio and 4 uncertain parameters that have to do with the physics, like with how much mass is transferred here, what this mass ratio per stability is, etc. And this is huge for population synthesis people, because normally we have to deal with like, I don't know, thousands of uncertain parameters, and they're all messy and it's all chaos. So having only 4 parameters to work with is great. That was really fun. So this kind of just shows that it works, where on the y-axis here I'm plotting the primary black hole mass, and on the x-axis the 0-H main sequence mass, which was what the function was of. And this gray is some fiducial binary population synthesis results. You already see it is indeed cutting off below some mass as a function of the mass ratio. And this is what we predict analytically for the cutoff to happen. And so now with triangles showing the 99th percentile of the population, seems to really be at least explaining the behavior of the population. And most importantly, so we're talking about neutron stars, you can see that under these assumptions, this minimum cutoff is above the minimum mass or the maximum mass of neutron stars. So you will just not form any binary neutron stars with this. And so stable mass transfer channel cannot contribute to binary neutron star formation. This result has also been found or retrieved by multiple other studies. This is from Yorio et al. With the 7 methods paper. This is the formation of black holes as a function, I think it's a function of metallicity for different physics. And you just have to look at the different colors, show which formation channel contributes what fraction. So pink is stable channel, contributes a lot. These are 2 forms of the common envelope channel, contributes another bunch. And then we go to binary neutron star formation. All you have to see is there's no pink at the bottom, no contribution from the stable mass transfer channel. Similar again here, work by Tom Wag, who was doing this with the simulations by Verboekhaarde, showing at the top the fractional contribution of different formation channels to binary black hole formation. It varies a lot, but there's a lot of pink. Very often the stable mass transfer channel dominates or contributes a significant amount. It never contributes to the binary neutron star formation. Okay, so that's cool. So for neutron stars, I feel like this is underappreciated, that we only have to worry about 1 formation channel. So that's kind of fun. But this prediction also has another interesting consequence. Because if you plot this same relationship, so maximum primary black hole mass is a function of Sam's mass ratio, but now for some different physics variations, so the colors are different physics, you can still predict there's a different cutoff at different places. And this then completely determines or influences where you predict the peak of the binary black hole or the peak of the stable mass transfer channel to be in a mass space. You can see that if you have a really high cutoff here, this dark green line, and obviously you introduce this large gap between the primary mass black hole coming from this channel and the neutron stars, whereas this yellow line has a much smaller gap. So if we now look at the gravitational wave population, so this is actual data from gravitational wave potential gap 3 in blue, showing the binary black hole population. There are features detected in a mass distribution. In real life, the features it's kind of a mess. Like data analysis is complicated, and which model you assume changes a little bit what your distribution looks like. But these 2 features have been found by a bunch of studies using all kinds of different methods. So I think currently these are the 2 features that we can really trust that are probably there. But I've been talking a little bit about this feature that seems to correspond a little bit to the other feature that I was just talking about, the stable mass transfer channel. But note again, and this is what the teacher was also already mentioning, is like this 9 solar mass peak is about an order of magnitude higher than the 35 solar mass peak. So you could ask, why are most black holes 9 solar masses? And now I'm going to pull this a little bit broader, but let's start with the gravitational wave still. So before I dig into this, I want to think about what it means that the binary black hole mass distribution peaks at 9 solar masses. Because you might think, okay, well, 9 solar masses, why not? Sounds good. But if you think about the IMF, then the progenitor, most likely progenitor stars of like 3 solar mass black holes are an order of magnitude more common than the most likely progenitors of 9 solar mass black holes. So in order to understand why is there a peak at 9 solar masses, you should also understand where are the low mass black holes. Where are the black holes with about 2-ish to 6-ish solar masses? And here's where I want to take it, broad and an agnostic view, even though this might sound familiar to some people. The first option is we just don't see them. Maybe there's an observational bias against detecting low mass black holes. And now that's true. There is indeed, we can't detect low mass objects as well with gravitational waves because we don't have the night volume. We don't probe the same volume. But even when correcting for that, it still seems like there's probably a peak-ish at 9-ish solar masses. Upcoming data will give us a much better update on this, but currently, let's just blow this one out and say, okay, let's assume it's really there. And the second option I'm going to talk about is what I've just been introducing you to. What if these black holes form with 3 low masses, but they don't per se make it into merging binary black holes? So maybe there's an evolutionary bias why the formation channel doesn't want to form double compact objects with these low masses. Now, this is what we just saw with, for example, the stable mass transfer channel, which predicts this naturally predicts a dearth of low mass black holes. But how do we know that that is really what's going on? Well, we should take this model and fit it to the data. And that's exactly what Jackson Godfrey, she's with Ben Farr, is currently doing. She's thinking about, can we use this as a strongly parametrized model for the data of the observed binary black holes and observed mass ratios and masses, and fit it to see if it works. So this is still ongoing, but I got pretty excited. This is also the reason I got into this project, by seeing some of her earlier work where she wasn't really asking the same question of does it come from stable mass transfer, but she was asking, what if I just plot the mass ratio distribution of gravitational wave data, and I distinguish between stuff that is in a 9 solar mass peak in blue and kind of the rest. And what you see is that the 9 solar mass the stuff that's in a 9 solar mass peak in the data seems to not peak at 1, but peak at like 0.6 or 0.7-ish mass ratio. And then this, ignore all the background, but this is from another paper earlier where basically the same mechanism that predicts that you have this kind of steep drop and low masses also predicts a very strong Gaussian at about 0.6, 0.7 of mass ratio for the stable mass transfer channel. So inconclusive, but helpful is what I would say. So stay tuned. Okay, yes, so this is all very encouraging, but there has been a third option flowing around for more than 20 years now, and that is, what if low mass black holes just don't exist. And the first time that this was proposed, this is known as the neutron star black hole mass gap. First time that this was proposed was in 1998 when there were like 6 X-ray binaries, and they said, oh, statistically it seems like there's an underabundance. And at the time that was, for the longest time not super certain. Some people believed it, but not everybody. And then in 2010 there were a couple of follow-up papers by Farrell Ozel and then Will Farr, etc., where they were redoing the analysis and confirmed really there seems to be a dearth of low mass black holes in the X-ray population. And this is why, but as soon as it was proposed, it's also always been very much debated. And this is why, if you've been following the archive for the last couple of years, there have been so many claims of black holes in the gap and the science papers that were disputed again right after, because a lot of these observed black holes in the gap turned out to be helium stars or restricted helium stars. Kareem al-Badri is maybe responsible for killing most of these systems. But then gravitational wave 230529 was announced earlier this year. And this beautiful black hole is it's a little bit dark here, but this beautiful infographic from Shanika. And this black hole is kind of smack in where we expect the mass gap to be. You could argue, in some parts of the cases, it's still a really massive neutron star. But I would say, okay, it definitely looks as if there's no inherent supernova reason as to why there really should be a gap. And it's also important to know that the theories that explain a gap between neutron stars and black hole were post-dictions onto the observations of X-ray binaries. Because supernova people predicted just a smooth distribution, and then the observers said, hey, look, we see a gap. And so supernova people started to say, okay, well, maybe there's a difference really between neutron stars that explode and throw off their outer layers and just form the iron core, and black holes that don't explode then and then just fall back. But this is really a big question mark and difficult, the whole field in itself, like the random masses and the kicks that you get from that. And okay, so basically this same month, April, everyone's like, yay, there's no gap. And then the same month, Kareem al-Badri came with this plot, which shows all the Gaia neutron stars. This is pulsar, so galactic neutron stars, X-ray binaries that we now have, which are of the order of 20 right now, and then some spectroscopic binaries that we've been detecting, and the Gaia black holes that you might have heard of. And so this is the mass on the y-axis, the orbital period. And so these are all wildly different populations. And if you draw a straight line here, you could once again say, maybe there is a gap between the most massive neutron stars and the least massive black holes. But if you now overplot on random, this is a little bit unfair because these are actually posteriors that are not per se completely like this. And I overplotted them at random periods, obviously just to show a point, but these are gravitational wave sources, the lowest mass gravitational wave sources with their 90% confidence interval. This is GW23, whatever the phone number was. And you can see, if you look at this already, it seems to be like, well, I don't know. Multiple of these seem to be falling inside the gap, so maybe there is no gap at all. But then the first question that should probably come to your mind is, well, are we really comparing apples to oranges? Are the populations of gravitational wave sources the same as the population of things that we see in the galaxy? And the first argument to say, well, maybe they're not the same population, comes from the metallicity. We know from all of these systems in the background, sorry, it's hard to find now, but all of the galactic ones, they're all pretty high metallicity, except for, okay, Gaia pH3, but we don't care about that for now. And people often say that all of the gravitational wave sources have to come from really low metallicity. But is that really true? This claim comes from results of the formation efficiency as a function of metallicity. This is something that people have been consistently finding over the last 6 years or so. So basically what I'm going to show here on the y-axis is formation efficiency, which is the number of merging double compact objects that you form per star formation, so per solar mass of stars formed, as a function of metallicity. Well, also here. And so if we look at the binary black hole formation efficiency, all of these different studies shown here in the bottom are plotted here using different codes, different setups, different physics assumptions, and still all of them kind of predict this flat behavior at low metallicities, and importantly, a strong tanking or multiple orders of magnitude drop at high metallicity, which makes people say you can never form merging binary black holes at high metallicity.
Question.
Yes.
Given that, why should we be taking seriously AGN disks as a source of binary black hole measures?
So this, you're making a fair point. These studies are all kind of thinking more about isolated binary evolution, not so much about AGNs.
But a lot of this has to do, doesn't it, affects mass loss on the probability of forming a black hole.
Yeah, so as I'm going to talk about right now, it is indeed a combination of mass loss and the radii that kind of mess up the formation channel. But why do you say that you would never be able to form in AGN disks? Your main reason why you form mergers is because you get like dynamical formation through, for example, migration traps that kind of catch these black holes, and that doesn't really matter depending on the
The question is, in a high metallicity environment, what rate of radiation? Because the metallicity will be higher than the local solar neighborhood. Sure.
Sorry, where will in AGN disk the metallicity will be higher?
Well, in AGN disks to be like higher metallicity.
Yeah, so I think that wouldn't really matter for this, because here you lose things either because they become unbound or because they become stellar mergers. I'll show that in the next few slides, but in AGN disks, you don't really care if they are from initial binaries that stay bound or become stellar mergers. You could get a stellar merger that just forms a big star, and then maybe it blows off a lot of mass because of the mass or the winds. But if it's stuck in the migration trap, it will just hang out there and stay there until maybe another thing falls into the migration trap. And so you can still form mergers in AGN disks at very high metallicities, I assume. But I'm not a...
If you want the black holes, and if the disks are kinetically quiet, right?
Yes, yeah. So there's the how long does the AGN disk live, and how long do these compact objects live, and can you still get them to get close together? Yes, that's a good point. That's a really good point. In fairness, I am mostly focusing more on isolated binary evolution here, where it does have a big effect also on dynamical formation, because a lot of these things, if they just get unbound and really exit the cluster, for example, then you lose them. But AGNs are the one environment where you wouldn't really lose them even if they get a large kick, because the potential well is so much deeper than it is for globular clusters or nuclear clusters or young clusters, etc. Okay, yes, but good question. You're actually going a few slides ahead. But let me first state the result. The result that people have been finding is that binary black hole formation heavily dependent on metallicity, like tanks at high metallicity. Binary neutron star formation, kind of messy, but not, strongly dependent on metallicity in any sense. All of these models kind of show straight lines with metallicity. And black hole neutron stars show somewhat intermediate results.
So sorry, just to try to understand that y-axis as number of events per mass of stars formed. So is that like -6 is 1 per ton of the 6 solar masses, or?
Yeah, so you form 1,000,000 solar masses, you would get, and the line, like, here it says if you, per 1,000,000 solar masses, you form like, am I saying that right? Yeah, 10 solar masses. So for 10,000 solar masses formed, you form one merging binary black hole at low metallicity. Yeah, and so that is merging here includes everything that's important that merges within the age of the universe. So it is kind of piling on different delay times. You can make it for different masses, different delay times, but if there's nothing to work with, then I just do it. Okay, so why does this function matter so much? Well, you might, if you followed this particular literature, you might have heard very often that the merger rate changes a lot. Actually, this comes back to your question as well, like why do they overpredict a lot? If you assume that the binary black hole formation does this sharp drop at a high metallicity, then the merger rate that you predict will be really sensitive to how much low metallicity star formation you assume that there is in the universe. And so there have been quite a few papers on the web showing that if you change the cosmic star formation history, you wildly change the merger rate. And that is a direct consequence of this function, because if it drops at slightly higher metallicities or at slightly lower metallicities, it will give you a huge difference in the predicted merger rate that you get. And so it's really important to understand that we understand why it drops and if we believe that drop. Same kind of idea is that if these binary black holes really only form at the lowest metallicities, that means they are really good tracers of low metallicity star formation, which is quite unique because most things don't trace low metallicity star formation. And lastly, if the binary neutron stars are indeed much less sensitive to this metallicity, then that also helps to make them good candidates for, potentially good candidates for spectral sirens. So I want to zoom in on this last bit a little bit. So just to get everyone on the same page, spectral sirens are basically, we're trying to measure H0. And so to do that, you need the luminosity distance and you need a redshift. Now distance you get directly from gravitational waves. And the redshift is more difficult. You could get it, for example, if you have an EM bright counterpart, but you could also get it from the redshifted mass. So the detected mass is the true mass but then redshifted. If you manage to break this degeneracy by saying, okay, but I actually really know what the true mass should be, then you can say something about the redshift. Or if you know how the mass distribution behaves, and for example, the mass distribution doesn't evolve much with redshift, then most of the redshift will be coming from the cosmological redshift. And so the hypothesis is that because neutron stars only come from one formation channel, and they're much less dependent on metallicity, they might be much less changing their mass distribution with redshift. Yes?
So just to poke on that point, in the previous slide, you showed that the formation efficiency is about metallicity. But that doesn't necessarily mean that the mass distribution.
That's true. That's true. So it is in this case true that the mass distribution doesn't evolve as much with redshift, but that is in part. So if you want something that's completely non-evolving, like the mass distribution to be non-evolving with redshift, you need to have one formation channel, and like not to have different formation channels with different masses pop up with different delay time distribution. So that check is checked because we expect only one formation channel to be there. Then you don't want the remnant mass function to be very metallicity dependent either. So not the same, like if the initial masses, the final masses, like how populated those masses are, thus matter a bit, like if your initial mass function, I don't know, is metallicity dependent, you will get more or less from a certain mass, but it wouldn't shift the peaks left or right, if that makes sense. Because the random masses that you get are still like 1.3 and 1.7-ish solar masses.
Practically speaking, how do you know that you've got neutron stars and not black holes? Is it
You don't,
because of the
but
mass, right? So
yes, you don't really. So indeed, if you're really going to do this experiment in real life, it will be a bit more complicated. You have to take into account that you're not entirely sure what are neutron stars, what are black holes, but what the spectral science cosmology will be is that you take multiple peaks and you say, okay, well, this peak is probably neutron stars. This is something that is more like black hole neutron stars and stuff like that. But the purpose of this paper was, this paper, Shunanra, again, the grad student I mentioned earlier, he was saying, okay, can we test this hypothesis and say, if we take our best guesses of what a neutron star mass distribution would be, so we take population synthesis of binary neutron star masses, and we inject them to try and infer the Hubble constant, then does it matter or does it make a difference if we assume that there's a correlated population, so that basically this is wrong. If the correlated population says like, okay, the real function is really mass ratio and redshift all together, the uncorrelated population says, no, you can fit separately the redshift evolution and the mass and mass ratio evolution. And what he showed here is that for all the variations that we explored, where we tried to kind of break this mass with redshift evolution, it doesn't even really matter. So the blue is the correlated and green is the uncorrelated, and that you see that and this is the number of detections, how well you can strain the Hubble constant with only binary neutron stars. It doesn't really matter if you assume that the population is correlated or not. They both give you about a sub% level precision after approximately 3,000 binary neutron star observations. So you might think, oh, 3,000, we're not there. That's true. This is really for assuming third generation detectors, which is also why this is a plug for third generation detectors, because at the top you see observation time in days, and okay, with the default assumptions from GWTC3, you expect only like 3-ish weeks are needed to get to 3,000 detections, which is ridiculous. Now, you can be very pessimistic and say, okay, well, this is super overestimated because, of course, we have not seen any neutron stars, so the rate is much lower. But even if the rate is much lower, you might have to wait like, I don't know, 9 months or a year, which honestly is still pretty good to get this kind of independent distribution. And so I think the main takeaway that I want to stress is not that I don't expect the neutron star distribution to ever not evolve with redshift, but I expect the mass distribution of neutron stars to evolve much less with redshift than the black hole population. Yes?
Just like a follow-up of that, do you assume like a fixed true mass distribution, or do you jointly infer that with your cosmology?
No, yes. So here the population, that's another thing that will make this would make that we have to wait a little bit longer. Here it was not a joint pop and cosmology inference. There were the population was assumed to be known, and then the real thing was to see if in this case you would introduce bias if you have a correlated or uncorrelated population. So in reality it will be more uncertain, but it might even matter less, like you have other uncertainties that will dominate over this uncertainty.
So best normalized, would the spectral sands give us information on compactness and time?
This is not my area of expertise. I would say, I think so, but I'm actually not sure. I would say that they might help. Well, I think if we understand the mass distribution very well, then we probably will also understand hand in hand the maximum mass better, which will help constrain the equation of state. So I guess it's not really the understanding the spectral sirens, but it's more understanding the masses.
A technique like this is independent of the electromagnetic
Yes,
counterpart,
exactly.
but requires many examples.
Mm-hmm.
So practically, do you expect this to give you the sub% measurement before a smaller number of counterparts gives you a sub% measurement?
Well, currently, yes, but this is obviously a guess. But I don't see, given how few neutron stars we've detected now, I don't see us really improving in the number of bright, like neutron star mergers with counterparts before their generation. Like 04 and 05, there is a good chance that we get 0 additional binary neutron stars with counterparts. And then when 03 is online, you will get these anyways. But in reality, obviously, we're going to do a joint thing with everything, right? We want to do spectral sirens, not just with neutron stars, but with the neutron stars and the black holes, and maybe all the features that we can get. And like also do the analysis from multiple angles, like do it just from the neutron stars, just from the black holes, with all features. As many angles that you can take and see if it introduces different biases.
Yeah, you could also do it with like the spin distribution and like not just the mass distribution, but like other things as well. That would give you even better constraints.
Yeah, yes, exactly, yes. So the more systems we have, the more interesting it will get. And I think this was just kind of a test, not even proof of principle, but just like showing like how many detections would you need to do this with neutron stars, and would you get a bias under our current best estimates, which are maybe not the truth, but some decent estimates. Would you need to know the redshift evolution, the correlated redshift evolution or not? Which is cool. Okay, so how long do I have left? 5 minutes? Okay, so this is the last question, the last thing that I am addressing. I've already been talking about it a little bit, but why is it that the binary black hole formation is so much more metallicity dependent than the binary neutron star formation? And so to answer that, I first want to go back to people who don't think about stars very often. Why do stars depend on metallicity in the first place? Well, at larger metallicity, we expect stars to be bigger. They have a bigger radius, they're puffier, and so they interact at different moments. And secondly, at high metallicities, radiatively driven winds in particular are stronger. So you have more metals, so you have more things that your radiation can grab onto, and then you get stronger up close. Now, these two seemingly simple single star effects have a whole wealth of secondary effects on the binary interactions and eventually the formation of double compact objects or not. And so the question that we tried to set out here was understanding which of these effects is dominant and why. And I think this is also why all of those studies that I showed you in the beginning, they all give explanations as to why the binary black hole drops at high metallicities, but they're often quite different and sometimes even contradicting explanations. And I'll get back to that in a second. But so what we did here was say, okay, we just take a big population of like 5 million binary neutron stars of double compact objects, and we evolve them exactly with the same initial conditions and assuming that they get exactly the same kicks and everything, and evolve them at different metallicities and see why some of the potential merging binary black holes at some metallicity will become binary black holes while at others they do not. So that's what this plot shows. Like it really shows that the binary black holes that you form in low metallicity. At high metallicity, they either become unbound, so they usually because one of them got a kick, or they become stellar mergers. And with black hole neutron stars and binary neutron stars, it's a bit more chaotic, but you can also see there's an exchange between the unbound and the stellar mergers. It's not, for example, what a lot of people sometimes still say, that at high metallicity, strong winds will widen the binary black holes, and so they have a too long delay time, and so they don't merge. They most often unbind instead of getting too wide to merge with it. But this information was still not enough, because it turns out that if you really want to understand this question, you have to split it again by formation channel. And this is why I think the literature has been having so many kind of conflicting results. If you look at all the formation channels in isolated binary evolution together, you get different answers. And it's most important here to note that, again, common envelope only forms, the binary neutron stars only form through common envelopes. And for example, the chemically homogeneous channel only forms binary black hole mergers. I'm going to skip through this quick. We repeated this game for many variations. Very importantly, we used new and updated wind prescriptions, also for red supergiant winds that people have not done for the longest time. And depending on which formation channel you think is dominant for binary black holes, you find a much less steep drop with metallicity. It still decreases at higher metallicities, but it's not this tanking behavior that we see here. And I think that it's mostly because everyone was using Nieuwe Huis and the Jager giant winds from '97, and there's a whole reason behind that. But I think that doesn't tank anymore. We repeated this for more points. Every point is kind of a simulation, and I'm just going to skip to the conclusions. Basically, per formation channel. For the homogeneous evolution channel, it really matters. The radius with metallicity is a really important point. For the stable mass transfer channel, it's a mixture of the radius and the winds. And for the common envelope, it's really mostly the winds plus kicks. So why is the binary neutron star formation not so metallicity dependent, at least in our simulations? Well, as I just mentioned, the common envelope channel mostly loses stars or loses potential mergers through this kind of winds plus kick effect. So this shows the same helium helium strip stars with different assumptions about the winds, like strong winds or low winds. And then if they get pushed below a certain mass, they're assumed to receive a kick. Now for black holes, we scale this kick with something like fallback, so that black holes that are really close to neutron stars in masses will receive a large kick, and black holes that are not very massive, receive basically zero kick. And so the closer you are to neutron star, the more unbound you are. However, for neutron stars, we don't really assume this linear or strong mass dependence. We just assume that if you're a core collapse supernova, get drawn from some Maxwellian distribution. It's quite broad. If you're electron capture supernova, you're drawn from a smaller kick distribution. And for this kind of is to match observations that show double peaks behavior in the velocities of neutron star kicks. Though I really want to stress that here, there's also no strong evidence that this is even related to electron capture supernova and core collapse supernova. We think probably, but don't know for sure. But so there's no direct relation between the more massive neutron star you are, the less massive peak you get. And I want to end with this because raising a question mark, do we even know that this is true for black holes though? Do we really know that more massive black holes should get a lower kick? Well, maybe you could make some theoretical arguments, but in reality, we don't know supernova. And these, if you plot all the kick velocities inferred for different masses of black holes, it's, a bit of a mess. It doesn't really say, you could draw a line like this, of course, but you could also draw a line like this, and can also draw a line like this, I don't know. It's, in my opinion, it's uncertain. that the black holes really get a linearly lower kick as you go to higher masses. So
Where do these measurements come from again?
these are all different. So the blue are X-ray binaries where people, to get the kick, you really need peculiar velocities and to make some assumptions about the binary evolution. So it's quite difficult. You need a whole paper for one of these systems to get some measure.
How many are actually from proper motions?
I think all of them have to have some proper motions in there. I think this one is a special case. This is like the microlens system. I don't really know how they did that one again. But all of them have some idea of the motions of
So
this.
it's not just, in some cases, you have some difference on the kick from the requirement binary remain bound to the stellar.
Yeah, although not really, but you do have to make strong assumptions about the previous evolution. So for example, Gaia BH3, this is under the assumption that it is coming from an isolated binary and that the eccentricity has to come from the kick. But there's many people who, rightfully maybe, believe that Gaia BH3 was not formed as an isolated binary, but from a cluster dynamics. Okay, I'm almost done. I really am. Basically, I'm just gonna say, we need more EM observations of black holes. We need to see black holes not just in gravitational waves, but in every wavelength that we can get our hands on. And I'm just gonna leave my summary slide up because I'm going way over time. So thank you all.
We had a lot of questions already, but this time for maybe one or two questions quickly before we go upstairs to science. Anybody?
In the plot that you're showing with efficiency with metallicity, how much of that is coming from the fact that all of the isolated populations in this course are pegging their rates to what we actually observe? In other words, is this like decline sort of a clustering effect?
Yeah.
Sociological clustering effect?
This is not a sociological, but it is actually one of the things that my takeaway for this work is that if I look at these plots, I think we're really overestimating the rate because this pink line, and we'll talk during the graphic meeting tomorrow a little bit more about that, but this pink line basically is what if we assume that every binary that interacts and has a mass high enough to form a binary black hole would form a binary black hole. And this line is really close. So this already shows that this is being the median from our population inference. This is like a factor 5 to 10 difference, which means that 1 in 5 of all binary black hole, of all binaries that could ever form a binary black hole do form a binary black hole. And to me, that is an immediate indicator that we're not saying binary black holes are threading the needle. We're saying they're super common, and that might be an overestimate.
It's even more apparent in the neutrons to neutron structure.
Yeah, so this is more chaotic, but this is, for example, it's a little bit unfair because obviously what I assumed for this pink line may not be completely the same as what everyone in the background formed, but I feel like I made reasonable assumptions here. And given that some of these lines touch this, that basically means doesn't even matter what you do for binary formation or binary interactions at all. Every binary neutron star that could have formed a binary neutron star will have that. So
It's also kind of suspicious that we have higher rate uncertainties with neutron stars, and just the band,
yes.
is wider there compared to.
Yeah, this just shows that these all form from the common envelopes, and what you assume for the common envelope system makes all the difference. And I think for me, a main takeaway is maybe this should just be an order of magnitude lower, and maybe our models are just being a little bit too optimistic just from this perspective.
Any last question? Okay, so let's thank Lieke again and